Hello, I welcome you all to this another interesting screencast. We are going to be solving this engineering mechanics problem, and it reads determine the distance y bar to the centroid C of the beam's cross-sectional area, and then compute the moment of inertia I x prime about the x prime axis. This problem is coming from the engineering mechanics statics textbook, 13th edition by R.C. Hibbeler. Right, so we have been asked to find the centroidal distance y bar as well as moment of inertia about the x prime axis. Moment of inertia I sub x prime about the x prime axis. Right, so in the previous video we worked on problem 1042, which was about finding moment of inertia about the x-axis. Okay, and then we worked on problem 1043. So we worked on 1042, which was about finding moment of inertia about the x-axis, and then we also worked on problem 1043, which was about finding the moment of inertia about the y-axis. Now we are on problem 1044. We are being asked to find y bar, which is the centroidal distance of this cross-section area, as well as moment of inertia about the x prime axis. So we are working on the two. So since we already did part of the work, which was finding moment of inertia about the x-axis and the y-axis, I'll just collect the work from my previous video so that we just start from entering the table to find the centroidal distance y bar and moment of inertia about the x axis, x sub ix prime. Okay, so for finding the centroidal distance y bar, this is equal to summation. Okay, because this is a composite cross section. Summation and is made out of regular shapes. So summation of y curl, these are the local centroidal distances to each particular area that we choose times the area, and then divided by summation of the area. So this is the formula we're going to use for finding the centroidal distance y bar. And then for finding moment of inertia I sub x prime, we are going to use the parallel axis theorem, which states Ix prime equal to the centroidal moment of inertia about the x-axis plus dy. This is the distance from the axis, in this case the x prime axis, to the centroid of each of the areas times area. Okay, so this is the formula we're going to use. We use this formula for moment of inertia about the x prime axis, and then we use this formula for finding the centroid distance. So I've done already part of the work to just reduce on time, just like I said, because I did the video, I did the 1042 video, 10-42, which you can check, and 1043. These are in the same video. All right. So now we are working on 1044. Right. So let's go to the next page. Great. So like I said, I did most of the work in my previous video. You can check it out. We had everything else written out. So I thought there was no need to write things that I already wrote in my previous video. So here we are. We've redrawn the cross-section area. And then we have defined, we have the shape 1, this one at the bottom, seen this one, okay, and then we have shape 2, this one, and then we have shape 3, this one, okay. And then for each one of these shapes, we have assigned them the centroidal distances with respect to the x-axis, the y curled distances. So we have a y curled 1, which is half of 30. which is half of 30. So y cubed 1 is equal to 15. Y cubed 2 is equal to 30 because we are measuring these distances with respect to the x-axis. And the reason we are doing this is because we want to find the centroid distance along the y-axis. Okay. So y cubed 2 is equal to 30. You see this 30 here, okay, plus half of 140, okay, hence this formula, all right, okay, which is equal to 100. And y cubed 3 is equal to, from the x-axis, is equal to 30 plus 140 is 170 plus half of 30, okay, then this gives us 185. Okay, 185, like so. Okay, so we have all these local centroid distances from each respective area. Then using this formula, like I said initially, y bar, I want to find y bar. Y bar is equal to summation of the local centroid distance times the area. We sum them up, there are 3 of them, then divided by summation of the area of each one over these particular shapes. Okay, so we have also found the area. We have the area 1 is equal to 200 times 30, which gives us a 6,000, right? Area 2 is equal to 30 by 140, okay, we've seen 30 by 140, which is equal to 4,200. And area 3 is equal to 100 by 30, which is equal to 3,000. So we have all the areas. And after finding the area, we also decided to find in advance the local moment of the centroid or moment of inertia for each particular area or each particular shape. So all these are rectangles. So for shape number 1, we have centroid or moment of inertia of an area. So Ix1 is equal to bh cubed divided by 12. Our b for shape number 1 is 200. Okay, the base 30 plus 170 is 200. So 200, the height is 30. So 30 cubed divided by 12, then it gives us a 0.45 times 10 to the power 6. Moment of inertia for area number 2 is base. The formula is the same. This is a rectangle bh cubed divided by 12. Our b is 30. Our h is 140 to the power 3 divided by 12. Then it gives us a 6.86 times 10 to the power 6. Moment of inertia for part number 3, these are centroid or moments of inertia, is equal to bh cubed over 12. Our b is 100, that's 30 plus 7 is 100. Then our height is 30, 30 raised to the power 3 divided by 12. It gives us a 0.225 times 10 to the power 6. Great. So with that information, let's start with the first part, which is finding the centroid distance. Like I said, we are using the formula y is equal to summation of y cubed area divided by summation of all the areas for the parts we've chosen. Okay, all assigned. Okay. So there we go. Let's enter everything here. So we have part. This is part. Okay. Then we have the centroidal, local centroidal distances along the y-axis for each of the part or the area. Then we have area. Then we have the product of centroidal distance times the area. So part 1, 2, 3, then summation. Centroidal distances, we have a 15. And then for number 2, area number 2, it is 100. For area number 3, it is 185. Area 1 is 6,000, just 6, 10 to the power 3. Area number 2 is 4,200, 4.2, 10 to the power 3. And area number 3, it is 3,003, 10 to the power 3. Alright, and the total area, if we are to sum up the area, 6 plus 4.2 plus 3. This gives us a 13.2 times 10 to the power 3. Let's get the products now of y cubed times area. 15 times 6 is 90, so this is 90 times 10 to the power 3. 100 by 4.2, it is 4,000, 420,000, which is just a 420, 420,000, 420,000, which is just a 420 times 10 to the power 3. And then 185 by 3 is a 555,000, which is just a 555 times 10 to the power 3. And if we sum up everything, 90 plus 420 plus 555, we get a 1065 times 10 to the power 3. And therefore, our y bar, like we said, is equal to summation of y cubed area divided by summation of area, which just gives us a 1065 times 10 to the power 3 divided by 13.2 times 10 to the power 3. So if we divide the two, then we have 13 divided by, we have a 10, not 10, sorry, we have 80.681818, so it's just 68, okay, 68 millimeters. Great. So that is our y bar, and if we were to show it here, it is going to be somewhere there. Let me draw it somewhere there. Okay. If we are to show this one with respect to it is going to be somewhere there like that. Okay. Oh no. Alright, let me indicate it. So this is the one here. This is our y bar is equal to 80.68 millimeters, which is this one here, okay, 80.68 millimeters. All right, now since we found this, what we need to find now are the distances. This is now our x prime, this is our x prime, this is our x prime axis, okay, so a new axis. So now what we need to find are these distances. We need to find distances from the centroid of each particular part to the new axis. Okay, so what I'm saying is we need this distance here, like here, for this one here, for shape number 1, if I was to show that, let me show that this is the distance that we are looking for. So if I was to extend this this behind like so, so we are looking for this distance there, okay, so that's the distance we are looking for. That is this distance here, okay, so that distance becomes we'll call it y prime cubed 1, okay, and the y cubed prime 1 is going to be equal to y bar, which is the centroid distance, minus y cubed 1, okay, which is equal to 80.68 minus, what is y equaled 1? Y equaled 1, we found it as 15, okay, right? So 15. So if we subtracted this, so we have 80 minus 15, this gives us a 65.68, okay, a 65.68. So we do the same also for the rest. So we need to find y prime curled 2, which is also equal to y curled. The reason I'm starting with this is because the other one is bigger, but if you don't mind, all values can be taken as moduluses, right, for this particular case. So I'll say y curled 2 minus y bar, okay, which is equal to 100 minus 80.68. This is equal to 100 minus 80.68. This gives us a 19.32. And then finally, we have where do I have space? Okay, all right there. And then finally, we have y curled prime 3 is equal to y curled 3 minus y bar, which is equal to 185 minus 80.68. This therefore gives me 185 minus 80.68. This gives me a 104.32. Okay, so there we go. We have all the information that we now need to use to find our moment of inertia about the x prime axis. So let's fit this in our table. So we have part, okay, then we have local moment of inertia about the x-axis for each area, then we have y prime curled, okay, then we have area, then we have y curled prime squared times area. So part 1, 2, 3 and summation. Okay, moment of inertia, centroidal moment of inertia of an area. For part 1, we found it as 0.45 times 10 to the power 6. Okay, all right. Let me just extend the spaces. The spaces seem to be very limited. All right, let me extend this line. I move this a little bit. Maybe there. Okay. Put this somewhere there like this. I think so. This will be much better because the spaces are very minimal. All right. So I think this should be fine. Let's move on. So moment of inertia. What do we have? For part 1, centroidal, we have 0.45 times 10 to the power 6, and then we have 6.86 times 10 to the power 6, and then we have 0.255 times 10 to the power 6, and then when we sum all the moment of inertia, we have a 7.535 times 10 to the power 6. And then the centroid or distance y called, this is y called, and we found these already. If you remember, these are the ones here, these ones here, these ones, we found this. These ones I'm highlighting, these are the values which are that we are just calculating. Y called prime. Okay, so what are they? So we have for the first one is a 65.68. Second one is a 19.32. The third one is 104.32. The areas we calculated already is 6,010, 6 times 10 to the power 3. Second one is 4.2, 10 to the power 3. Third one is 3, 10 to the power 3. And then the products, 65.68 squared times 6. So this gives us a 25.883 times 10 to the power 6. And then 19.32 squared times 4.2, we get a 1.568 times 10 to the power 6. And then 104.32 squared times 3, we get a 32.648 times 10 to the power 6. Okay, let me write this properly. Times 10 to the power 6. If we sum up all that, so we have 25.883 plus 1.568 plus 32.648. This gives us a 60.099 to the power, times 10 to the power 6. Therefore, moment of inertia about the x prime axis is equal to centroidal moment of inertia plus y curled prime squared times area, which gives us a 7.535 times 10 to the power 6 plus 60.099 times 10 to the power 6. Okay, and then finally our moment of inertia is going to be equal to, if we sum up all that, we will have a 67.63 times 10 to the power 6 millimeters to the power 4. Alright, so let me write down the summary here. So we have y bar, which is equal to 80.68 millimeters, and then moment of inertia about the x prime axis is equal to 67.63 times 10 to the power 6 millimeters to the power 4. Okay, so this is about it. And I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. I'll share the other videos and even the video I was talking about, the 1042 and 1043 video, which is a continuation of this video. Bye bye, and see you in my next screencast.